Welcome to AI Podcast. I'm Daniel, and today we're unpacking a NeurIPS 2025 paper called Fast Inference for Augmented Large Language Models.
I'm Maya. Give me the headline first. What's the one-liner I should remember?
They speed up tool-using language models by predicting what each request will do around its tool calls, picking a smarter way to handle the model's memory during those pauses, and then scheduling requests by how much memory they'll occupy over time. Faster replies without changing the model itself.
Tool using meaning the model pauses mid-answer to hit a calculator or a web API, right?
Exactly. And those pauses make serving tricky because the model's short-term memory, the KV cache, eats GPU space. When a request calls a tool, the server has to decide, do we keep that memory on the GPU, drop it and rebuild later, or park it on the CPU for a bit?
Like packing for a flight. If the layover is short, keep your bag with you. If it's long, check it so your hands are free.
Perfect analogy. The paper's insight is to make that luggage decision up front and let it drive scheduling. Instead of first come, first served, they rank requests by a score that's basically memory over time. Think of it as giving the cafe table to the party that will use the least space for the shortest time.
Nice. Does the system have a name?
In the NeurIPS version, they call it Mars. Earlier drafts used lamps, but the core idea is the same.
Who's behind it?
Lead author Rana Shahout and colleagues at Harvard with collaborators from Tsinghua. Minlan Yu is among the senior researchers.
Got it. Now, why was this needed? What were people doing before?
Serving stacks like VLLM are great for standard requests, but they assume length predicts runtime. With tools in the loop, that link breaks. A short prompt might block forever on a slow API, and a long prompt might breeze through if its tool is fast. A prior system called Inference made better choices about keeping or dropping the cache, but it still processed jobs in arrival order, so head-of-line blocking remained.
So the new approach ties two things together. Predict the near future for each request, and then schedule with that knowledge.
Right. They predict two quantities. First, how much text the model will generate before the first tool call. Second, roughly how long that tool will take based on its type. Using those, they choose keep, drop, or swap for the cache, and then compute the memory over time score to rank the queue.
How do they train those predictions without overcomplicating the system?
They use a small helper model to estimate the pre-tool text length and simple class averages for common APIs to estimate duration. The point isn't perfect foresight, it's good enough to avoid obviously bad choices, like hoarding memory for a request that's about to disappear into a long tool call.
And how did they test it?
They implemented everything on top of VLLM, tried mid-size open models like GPT-5 and Vicuna, and used tool use workloads, including a large benchmark of real-world APIs. They compared against Inference and plain VLLM and looked at end-to-end latency, time to first token, throughput, and the long tail.
And the results, in plain English?
Consistently faster. Think drops of roughly a third in overall latency, sometimes much more depending on the workload, and noticeably quicker first tokens when the server is busy. The gains grow as load increases, which is when first come first served tends to struggle most.
That cafe image really helps. Seat the quick, small groups first, and the room breathes. But what if their predictions are off? APIs can be spiky.
True. They show that within their setup, timing is fairly predictable by API type, so the estimates work. If reality shifts, small errors rarely reshuffle the ranking, and big errors mostly punish the one request, not the whole system. Still, in production, I'd add online adaptation so the timing estimates track live behavior.
Any other caveats?
A couple. The experiments are single server with a few GPUs, not a multi-tenant cluster. We don't see cross-model fairness policies or preemption. And the memory over time score is a heuristic. It's great for utilization, but if you have strict fairness or premium tiers, you'll want guardrails so tiny jobs don't always cut the line.
How does this compare head-to-head with Inference in one sentence?
Intercept picks a smart cache move but keeps first come, first served. This work picks the cache move and the run order together, which is where the extra speed comes from.
If I'm an engineer running an agent that hits web search, a code interpreter, and a calendar API, what's the practical recipe?
Add a lightweight predictor for pre-tool text, keep rough duration estimates per tool type, choose the cache policy before you start decoding, and schedule by memory over time rather than arrival order. You'll likely see quicker first tokens and better throughput without touching the base model.
Future directions you're excited about?
3 stand out. First, adaptive control that updates API timing on the fly. Second, cluster-level scheduling that balances multiple models and tenants. Third, planning for entire tool chains, not just the next pause, so the scheduler sees the whole conversation graph.
Right, and maybe a cost-aware mode too, because faster isn't always cheaper.
Exactly. Quick takeaway to close. Augmented language models pause to use tools, which breaks naive scheduling and wastes GPU memory. Predict a bit, plan the cache, and schedule by memory over time, and you get smoother, faster answers.
Clear, actionable, and very cafe-friendly. This is AI Podcast. I'm Maya.
I'm Daniel. Thanks for listening and see you next time.